To the next result, the Chinese remainder theorem. It essentially enables us to solve systems of congruences. Now onto the claim. So let W1 through Wn be natural numbers and be pairwise distinct. Moreover, let U1 through Un be integers. They can be any integers. There are no restrictions on them. Then if we denote capital M as the product of all the W's, or rather, let's denote it capital W, that will make much more sense. Then there exists precisely one X in the set W minus 1 satisfying the following systems of equations or congruences. X is congruent to U1 modulo W1. X is congruent to U2 modulo W2. Up to X is congruent to UN modulo WN. Now, how do we go on about proving this? The proof is surprisingly simple. Now, proof. We shall divide the proof into essentially proving two separate claims, as one might expect. First, we shall prove that the solution is unique if it exists, and then in the latter part, we shall prove its existence. And surprisingly, we shall use the uniqueness in the proof of the existence. So that's something to look forward to. Now, suppose we had two solutions, so uniqueness. Assume we had two solutions to the system of congruences X and Y. Well, this by definition means, well, satisfying also all the requirements. So this means two things. One, both X and 1 belong to the set of W minus 1, or rather the set of all integers through 1 to W minus 1, and that they satisfy the congruences, so that X is congruent to Y is congruent to UI mod WI for all I. Well, we can since both X and Y are congruent to the same number under the modulo of WY, that means they can only differ by a multiple of WY. In other words, this means that WI divides X minus 1 in absolute value. We're only dealing with positive integers here. For all I. But then, In particular, the product of all w divides x minus y. But this is equivalent to saying, by definition, that capital W divides x minus y. But we know that both x and y belong to the set of all positive integers smaller or equal to w minus 1. So both of them are smaller than w. So that difference is also smaller than w. So we have some large number dividing a smaller one. Well, this means then the only way this could make sense is if x minus y was 0. And this means that x is equal to y. And we have thus proven that if the solution exists, it is unique. We shall now have a look at the existence. And as I have mentioned before, surprisingly enough, we used the uniqueness result to prove the existence. We shall consider a rather perhaps strange construction at first, but it shall prove most useful. So consider the modular map mu, and it's the map mapping all the elements from all the positive integers ranging through 1 to negative w minus 1, and maps this into the following Cartesian product. So that will be w1 minus 1 by w2 minus 2 by dot 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 until wn minus 1, pardon me, wn minus 1, or in more compact form like this. Alright, well, why are we doing this? This looks awful. Well, because we define it in the following fashion. We map any given x onto the x modulo w1 x mod w2 until x mod wn. So why are we doing this? This looks horrible. Well, my friend, because we have essentially proven in the previous section, the uniqueness section, that this map is injective. Right, that's essentially what the uniqueness section says. And since here we have only a finite number of elements, and so we do here, then we have an injective map which maps a finite domain onto a finite codomain. Well, that means that it's onto as well. It's also surjective. And since it's injective and surjective, it is bijective. So from the uniqueness section, we know mu is injective, since the domain and codomain of mu are finite. Mu is surjective. it is bijective. So mu is an isomorphism, and now we make a key observation. Essentially, X solves our system of congruences if it is mapped. So X solves, or X is a solution if mu of X is equal to u1, u2, un. But this lies in the codomain, and we are dealing with a bijection, and as such, it must have a preimage then. And this means that since mu is bijective, the preimage of u1 exists and lies in the domain, the solution. And this concludes this rather beautiful proof.